to you in Yuda's old department, in fact. Um, so I think as we're all aware, Southeast Asia is very vulnerable to sea level rise. There's two things which I'd like to point out in this map. The first one is if we look at the ocean bathymetry, the depth of the ocean in this region, we see that it's very shallow. So this is indicated by this light blue shading all across the Sunda Shelf, uh, covering Indonesia, where I am in Singapore, Malaysia. And when sea level was a lot lower than it was today, during the last glacial maximum, there was so much water was locked up in large ice sheets, which no longer exist. And because of that, sea level was 100, 120 meters lower at some points in history. And what this meant is that this Sunda Shelf region was not below sea level, but actually above sea level. So the islands that we're so used to today, like Java, Sumatra, Singapore, in the past, these would have been connected. So we see that sea level changes in the past have really influenced the geography of the region, influenced the Southeast Asia, which we're now used to. And so perhaps it should not be a surprise that as sea levels continue to rise as a result of anthropogenic climate change, that changes in sea level will continue to impact this region. So now if you look at the light cyan turquoise shading across many of these coastlines in Southeast Asia, and even parts of countries that are currently quite far from the coast, this is showing the areas of land that could be inundated at high tide under a sea level rise of 2 meters. So we see that many of the Southeast Asian coastlines are very vulnerable to future sea level rise. Now, a sea level rise scenario of 2 meters during the 21st century is a worst case possibility. It's very unlikely to happen, especially during our lifetimes. That's something which we'll talk about soon. But I do want to say that sea level will continue to rise beyond the end of this century. And it's because sea level responds very slowly to global warming. So we get this slow, delayed effect of the sea levels rising slowly, even based on past warming. So sea levels will continue to rise for a long time in the future. One of the big uncertainties, though, is the future rate of sea level rise. So we don't know how fast sea level will rise. We don't know how much it will rise during the 21st century. So the magnitude of sea level rise remains very uncertain due to these complex global, regional, and local processes. So let me introduce 3 of the more important processes. The first is vertical land motion. Now, this is not the effect of climate change. Generally, vertical land motion is a local effect or a regional effect. It can be caused by different things, including earthquakes. So tectonics can play an important role in this region, and that's an important area of research. Another really important effect is land subsidence within cities. So a common problem for many coastal cities in this region is the extraction of too much groundwater for human use. And then cities can sink as a result. And when the city sinks, when the land goes down, even if there's no global sea level rise, then the sea level rise will rise relative to the land surface. Which is why we often talk about local relative sea level rise, because what's important for people, for residents of these communities, is how much the sea level is rising relative to them. Now, this vertical land motion or VLM effect can be very irregular, very inhomogeneous spatially and also in time. So you can get some places can be sinking very fast, but then just a few kilometers away, maybe it's not sinking as fast. So this is really important to consider locally, especially at the city scale. The second important effect is global in nature, and it is thermal expansion. As the oceans are warming, the ocean heat content is going up, and the ocean is expanding as a result. And this causes what we call a thermospheric sea level rise. Now, the thermal expansion coefficient varies a lot depending on the water temperature, the exact location of the pressure, salinity, and so on. The really interesting thing, though, is that when you average this effect globally, you can come up with a globally representative thermal expansion coefficient. And averaged globally, the thermospheric sea level rise is approximately a linear function of the change in the ocean heat content. So if you can project ocean heat content changes and you can estimate using climate models that thermal expansion coefficient, then you can project thermospheric sea level rise. There is some non-linearity that we've found, but to a good approximation, it's approximately linear. What's a lot less well understood, a lot more uncertain as a result, is ice sheet mass loss. So as the world warms, we expect a lot of ice to melt in Greenland and West Antarctica, possibly in East Antarctica too. And there's so much water locked up in the ice sheets that as they melt, as that water is added to the ocean, the mass of water in the ocean increases, and this can drive sea level rise globally. And this is responsible for many of the, well, the very largest uncertainties in future sea level rise. Apart from possibly the uncertainty associated with our human anthropogenic emissions of greenhouse gases. So I think this is an appropriate point to dig a little deeper with what I mean by uncertainty in this talk. What kinds of uncertainties am I talking about? What kinds of uncertainties are important for projections of sea level rise? So the first kind of uncertainty is scenario uncertainty associated with our future greenhouse gas emissions, We don't know how effective global agreements will be. There's lots of uncertainties about future technology changes, government policies, human consumption patterns. So we don't know how much we'll emit. And that's referred to as the scenario uncertainty, which influences the forcing on the climate system. For any given scenario and for any given greenhouse gas forcing on the climate, we don't know exactly how the climate system will respond. So we refer to this as climate uncertainty. When we're talking about climate uncertainty, we're thinking about things like the equilibrium climate sensitivity, regional climate change for any given amount of global warming, and so on. So lots of things are included within this climate uncertainty. But then for any given change to the climate system and any regional climate change over Greenland and Antarctica, we don't know exactly how the ice sheets will respond to that warming. And this is what we refer to as the ice sheet process uncertainty. And this is really where lots of the largest uncertainties are. We understand quite a lot about the ice sheets, but there's lots of possible processes like marine ice cliff instability that we just don't really understand very well, if at all. So the uncertainty here is very large. If we want to try and sample, to try to understand just how large each of these sources of uncertainty is, we can use different approaches. But one of the common, very standard approaches would be to consider different forcing scenarios, so different future emissions scenarios. So these give us plausible samples of future emissions. We can then use those to force ensembles of Earth system models. And if we have lots of different global climate models, Earth system models, this enables us to come up with some sort of estimate of how large the climate uncertainty is. And then we can use those Earth system models to force ensembles of ice sheet models. And then the ice sheet models give us some sort of estimate of the uncertainty associated with the ice sheet response. Now, there is a big caveat here. Because of the fact that these ice sheet model ensembles only account for better understood ice sheet processes, it's quite likely that some of these model ensembles are underestimating the total uncertainty range, which then poses a major challenge for projections. So if we want to actually make projections of sea level rise, we have to take into account these different sources of uncertainty and put different things together, basically, taking into account diverse processes across the whole climate system. The state-of-the-art sea level projections have been produced by a large international team that I was not involved in at all, but they've done an amazing job that makes my job a lot easier. So this is Bob Kopp and colleagues have led this effort to develop a modeling toolbox, a framework for assessing changes to sea level called FACTS. And this framework is essentially the same one that was used to produce the projections for the most recent IPCC 6th assessment report. So whenever I talk about IPCC or AR6 in this talk, I'm always referring to the sixth assessment report, produced by Working Group 1 in particular. And what this facts framework does is it has a simple climate model to account for the climate uncertainty in the climate stat. It then uses that climate forcing or the global climate warming and ocean heat content and things like that to then drive other statistical models that account for different processes. So the different processes contribute to different sea level components, as we call them. So when we talk about sea level components, we mean things like the Greenland ice sheet component, the West Antarctic ice sheet component, thermal expansion, thermospheric sea level rise, vertical land motion, and so on. And the projection for each of these components is probabilistic, which means that the uncertainty is represented as a probability distribution. And then facts would add all of these different components together to come up with total sea level rise. So this is referred to as the integration step, where these different components are combined to project total sea level. And again, facts, these IPCC projections, use probability distributions to represent that uncertainty. So whenever we talk about probabilistic projections, we're talking about probability distributions that represent scientific uncertainty. The challenge, though, is that depending on the assumptions you make and the methods you use to come up with these projections, probabilistic projections, you can end up with quite different probability distributions. So this is shown in this figure here. These are four different projections, all from the IPCC, from facts. They're projections of global mean sea level rise under very high emissions for the year 2100. And each one of these lines is a probability distribution. So a quantile function or it's basically an inverse cumulative distribution function, CDF. So they're probability distributions because they're saying that there's a small probability of remaining below, say, 0.5 meters. But then there's a really high probability of remaining below 1.5 meters, for example, here. Generally, the higher the line is, the higher the sea level projection is on average. And the steeper the line is, the more uncertainty there is. So this light blue line, workflow 1E, has much smaller uncertainty than this dark red line of workflow 4, which has a really large uncertainty range, a very long upper tail. Let me explain then what went into each of these different projections and what's driving the differences. So at the bottom, with workflow 1E and workflow 2E, for the ice sheet components, these used large model ensembles and then built statistical models on top of those ice sheet model ensembles. And these projections are referred to as medium confidence projections because they take into account what the IPCC calls medium confidence processes, which are processes that are a bit better understood. So here, medium confidence basically means better understood. Then low confidence processes would refer to possible processes that are really poorly understood. They're ones which have been hypothesized, but ones which are difficult to quantify, difficult to even prove that they will really influence things like ice sheet melt in future. So the low confidence processes include things like marine ice cliff instability, or MICI for short, that could lead to more rapid melting of the ice sheets. And those low confidence processes are taken into account in workflow 3E and workflow 4 at the top here. So we refer to these as low confidence projections, these two. Workflow 3E uses one Antarctic ice sheet model that represents the MICI marine ice cliff instability effect. Workflow 4 takes a very different approach and used structured expert judgment, where they asked lots of experts what they thought future ice sheet contributions to sea level rise could be in this century in particular. So the key takeaway here is alternative methods can be used to derive alternative ice sheet components of sea level rise. When we combine those into total sea level rise projections, we come up with alternative probabilistic projections that vary widely, and they vary widely because of these poorly understood ice sheet processes that are difficult to model. This leads to a challenge, or led to a challenge for the authors of the IPCC report. They did an amazing job because they communicated the ambiguity associated with future sea level projections. So this ambiguity is the fact that we can't come up with a single probability distribution that everybody agrees represents the uncertainty in future sea level rise. So because these poorly understood ice sheet processes are difficult to model, because the medium confidence and low confidence projections differ, you get this ambiguity. And this meant that the IPCC authors didn't come up with a 5th to 95th percentile range, because this so-called very likely range in the IPCC terminology. And this was a very honest result, because they didn't have one set of projections that they really trusted to give them that very likely range. They did, however, trust the medium confidence projections for the more likely central possibilities. So the official median projections and the likely range from the 17th to 83rd percentiles are based on those medium confidence projections. And then they used the low confidence projections to come up with two low likelihood, high impact storylines. So these were the very high sort of worst case possibilities they considered. But they didn't come up with an estimate of the likelihood or the probability of these high impact storylines occurring. And there was no 5th to 95th very likely range. So this is a challenge we've sought to address. We've trying to fill in this gap, transitioning between the center of the distribution and these possibilities in the tail. So our approach was to develop a fusion approach that fuses the complementary strengths of the medium and the low confidence projections in order to quantify the full distribution of uncertainty. So we want to combine these different projections to come up with a best guess probabilistic projection. Our fusion is shown in the middle here. This is all for the very high emission scenario, but I'll show you results for low emissions a bit later. What the fusion does is in the center of the distribution, for the more likely future possibilities, it follows the medium confidence mean. And then in the tails of the distribution, it follows the low confidence projections, and then just smoothly transitions between medium confidence and low confidence possibilities. This approach is essentially applying an additional layer of expert judgment. I want to emphasize that expert judgment is not something we should be afraid of. Expert judgment is necessary in science. It adds value, and it's completely unavoidable when we make projections of future climate change. Because expert judgment is used throughout the whole process of making projections, experts need to develop the models and the methods that are used to make climate projections. Experts need to select which of those projections are more reliable and can therefore inform scientific assessment, like the IPCC report. And we're just proposing we just add an additional layer of that expert judgment to consider the alternative complementary strengths of these different alternative projections. Digging into a bit more detail about our assumptions and how we do this. Mathematically, our fusion approach uses a weighting function and a trapezoidal weighting function that transitions between the medium confidence and the low confidence projections. And this is based on two key assumptions. The first assumption is that the model-based medium confidence projections reliably sample the more likely central possibilities between the 17th to the 83rd percentiles. So this is fully consistent with IPCC AR6 and their choice to use that central part for the likely range. Our second assumption is we're assuming that the low confidence projections provide additional information that's providing a more reliable estimate of unlikely tail possibilities because they're considering possible processes that the models aren't including. So in the extreme tails, we're using the low confidence. In the center, we're using medium confidence. And then we're smoothly transitioning between the two, in particular from the 83rd percentile up to the very top of the tail. So this has enabled us to quantify a best estimate of scientific uncertainty using a probability distribution. And because we have that full uncertainty range, it's providing a meaningful, very likely range between the 5th and 95th percentiles. It's still conditioned on a particular emission scenario, though. So we're not trying to assess the emissions uncertainty. We're just taking different possible emission scenarios. At least in this work, that's what we're doing. So on the left here, we have the low emissions scenario that's probably a best case possibility if we can really keep emissions low. And on the right, we have very high emissions, SSP 5 8.5, which should be seen as a worst case possibility. It is very unlikely, actually, that our emissions will be this high, but it's possible. So the dark lines are showing the best estimate, the median projection for the fusion. Then the darker shading is showing the likely range that's approximately consistent with the IPCC. And then our new contribution is this very likely range shown in the light shading, which is just showing how uncertain future sea level rise is, especially under very high emissions. There's this very long upper tail, so we can't rule out 1.9 meters of sea level rise this century, though it's far more likely to be lower in the 0.5 meter range. Now, I really like probabilistic projections. I think for scientists, they're great, and also for decision makers who are used to dealing with probability distributions. But they can be confusing for many. So we've tried to take a step beyond this. So using our fusion, we have now tried to come up with a few more user-friendly projections. So we're doing 5 different projections. So including a central best estimate projection, low and high projections, and then quite extreme worst case high end and best case low end projections. And our main contribution, because we're using the fusion that tells us about the tails, is for the worst case high end and the best case low end projections. So the worst case high end follows the upper end of that very likely range under very high emissions. That's shown on the left here in this dark red dashed line. Then the best case low end follows the bottom end of the very likely range under low emissions, and that's shown by this dark dashed green line, that green line here. And then the central low and high projections are somewhere in the middle based on the likely ranges. For global mean sea level rise, this table is summarizing those results in this column. The definition of the different projections is on the left. And then on the right, we're estimating the exceedance probabilities, so the likelihood of each of these different projections. And this is something we can do because we're dealing with a probabilistic projection for our fusion approach. Now, if we look at the low end and then look at the high end, this is giving us the best case and the worst case possibilities. It's possible things could be outside that range, but extremely unlikely. And that plausible range we're getting is from around 0.3 meters up to 1.9 meters of global mean sea level rise by 2100. But again, I do want to emphasize this should be seen as a worst case. If we look at the exceedance probabilities of that high-end projection of 1.9 meters, under very high emissions, by definition, there's only a 1 in 20 chance of reaching or exceeding 1.9 meters. Under low emissions, that goes down to 1 in 725, so is extremely unlikely. So it's much, much, much more likely that future sea level rise will be in this low to high range of 0.3 up to 0.9 meters, and the best estimate of around 0.6 meters, which is the central projection. But this is for the global mean. When we look regionally, things can be a bit different, and the uncertainty ranges are larger because there's more processes contributing uncertainty. So these are results that we've produced for the high-end projection for different cities globally, paying particular attention to large coastal cities, most of which are actually in Asia. So this is the high-end projection, and it's not showing the absolute numbers. Here we're just showing the difference compared to the global mean. So the global mean high-end projection was 1.9 meters. Here, if it's red, it's saying that the projection is higher than 1.9 meters. So we see across Asia, we see a lot of red. It means that the high-end projection for these Asian cities is 10, 20, 30, sometimes 40 centimeters above that global mean high-end projection. So for most of these cities, the high-end projection is above 2 meters. This is because of two main effects that are contributing to this elevated projection in Asia. One of them is vertical land motion, which is poorly constrained in this region, so it's adding additional uncertainty. The other effect, though, and this is really important actually for us in the tropics, is that the further you are from the ice sheets, when mass is lost from the ice sheet, the more of that water will come towards us because of some effects called gravitational, rotational, and deformational effects, or GRD for short. So the irony is that for us in Java, in Singapore, because we're a long way from the ice sheets, we're going to get a little bit more water from the ice sheets than places nearer the ice sheets would do. So this can lead to elevated high-end projections in Asia and across the tropics as well. So we should really care what happens to the ice sheets, even though we're so far away. If we then look at the other end, so we look at the best case low-end projection, we sort of see the opposites in that across Asia, with the exception of one or two cities, I think Manila here, because it has quite a lot of subsidence. For most cities in Asia, we have a low-end projection that's actually lower than that global mean projection. This could mean that actually a sea level fall is not implausible locally in Asia, though again, it's very, very unlikely. This is the best case. The reason why this projection is lower in Asia than the global mean is again to do with the vertical land motion. So the ice sheets aren't really playing a role here, but vertical land motion is. And it's because across Asia, the vertical land motion is very uncertain. It's poorly constrained how much the land height will change in future. So the more uncertainty you have, the wider your uncertainty range is. So then the lower your low-end projection is and the higher your high-end projection is. So let me emphasize that VLM, vertical land motion, is really, really important it's really poorly constrained, and there's a lot more work to be done on this component in this region. It's a massive challenge. In these projections I've just shown you, we've only taken into account regional trends in the vertical land motion. So these projections may not fit very well for cities that have a lot of local vertical land motion. So we've not accounted for intra-urban variability, especially the fact that for some cities, some parts are sinking a lot faster than other parts. So detailed city level studies are going to be really, really important when it comes to trying to understand the impact of sea level rise on any given city. We've also not taken into account variability in time. So a common assumption with VLM is that we just look at historical rates and then just extrapolate those into future, which for some large-scale regional processes may work. And it's probably the best we can do, actually, if we're wanting to do global scale studies. But we know that in cities, groundwater extraction can vary. In cases where governments have come up with policies to effectively limit that groundwater extraction, cities often stop sinking, or at least the rate of the sinking subsidence has decelerated quite substantially. So local government policies play an important role here within cities. The other thing which we've not taken into account here is tectonics and the possibility of earthquakes. So for locations quite near fault lines, which we have a lot of in this region, you might get quite substantial vertical land motion changes based on future earthquake patterns. I haven't done really anything in this area, but I have colleagues at NTU who've trying to understand some of these other possibilities in future. So to summarize this part of the talk, which is the main part of the talk, we fused the complementary strengths of these alternative probabilistic projections from the IPCC. We've then used the fusion to derive plausible worst case high-end and best case low-end projections, and some projections in the middle as well. The worst case high-end projection is elevated for Asian megacities. We should really care what happens to the ice sheets. And the plausible range reveals just how uncertain future sea level rise is across this whole region, even more so than globally. And globally, it's a very large uncertainty range as well. Before we move to Q&A, I'll very briefly introduce two other pieces of work, just in case this is something you're interested in and would like to learn more about. When I mentioned earlier about how different sea level components, like the Greenland ice sheet components, the West Antarctic and East Antarctic ice sheet components are combined, when you have probability distributions and you sum them together, you need to make assumptions about the correlation between those different probability distributions. So here we need to make assumptions about whether the uncertainties in these different components are correlated. And this is something which we've tried to dig into a bit more a bit more detail for the East Antarctic and West Antarctic and also Greenland ice sheets, considering that possibility of correlated uncertainties. And to do this, we analyzed a large multi-model ensemble, mostly from ISMIP-6, with some other published ice sheet model results that we just pulled in as well. And this analysis of this large ensemble has revealed strong correlation between the East Antarctic and West Antarctic ice sheet components. So the uncertainties are correlated. And if we neglect this correlation when we combine them, then we can underestimate the combined uncertainty. So it means that at the 95th percentile, this can be around 10 centimeters plus minus. The second piece of work is completely unrelated to the ice sheets. This one is focusing on how we use global climate models to project ocean changes like ocean heat content and thermospheric sea level rise. So when we want to project thermospheric sea level rise, we often use global climate model ensembles. The challenge with thermospheric sea level, ocean heat content, and most ocean variables is that you have drift in the climate model simulations. So this drift refers to spurious trends in the output data. There can be good reasons for the drift, genuine physical reasons, like the fact that the deep ocean takes a long time to reach equilibrium for any change in climate forcing. So even before anthropogenic climate change, the climate system might not have been in equilibrium, the deep ocean might still have been responding to past climate changes, including glacial cycles. But in climate models, you can also have unphysical reasons, so energy imbalances that shouldn't be there. And that can lead to these spurious trends as well. So you can correct the drift in a post-processing step by looking at the trends in the pre-industrial control simulations. But what we've argued is that this whole drift correction process has uncertainty associated with it. So we refer to this as drift uncertainty. And we came up with a technique to try to quantify this called Monte Carlo drift correction. And we find that for historical thermospheric sea level rise in CMIP6 models, that drift uncertainty can contribute 3 to 24 millimeters of uncertainty in the sea level rise during the historical period, depending on which global climate model is being used. So this is probably important for analyses of historical sea level change, but compared to the uncertainties with the ice sheets and emissions in future, this drift uncertainty is very small, so we don't need to worry about it too much for global mean variables, at least. That's all I wanted to say, so I'll just leave this summary slide up. And I welcome any questions or comments that you might have. Thank you.
All right, thank you, Benjamin. I always enjoy your talk. Very articulated, very eloquent as usual. I think we all agree on that. Let's go to the Q&A session, and as usual, I'll pose the first question. So I have two questions, Benjamin. So the first one is what causing the difference within the medium confidence and the low confidence, the expert judgment, how the probability can be differ with the one come from the model. So that's my first question. So the second question is how does the ice sheet probability that you are looking at, how is it compared to the other component, especially the manometric component? I mean, how is the performance of those components actually? because you mentioned the model is kind of empirical model for the doing the simulation. Yeah, maybe those two first from. Thank you.
Okay, thank you, Yuda. So if I understand the two questions, the first question is what's really driving the differences between these different ice sheet projections? And then the second one is how does the ice sheet's components compare with other components, both in terms of uncertainty and performance? Is that correct?
Right, right.
Yeah. Okay. So let me answer the second question first, as a way to lead in to the first. So we have these different components which are due to different processes. Because different processes are involved, the uncertainties vary quite a lot because some processes are relatively well understood, others are less well understood. So if we consider processes that are not the ice sheets, locally for vertical land motion, as I say, I think it's really poorly understood, especially in this region, and it's really difficult to project. So that one, I think there's a lot more work to be done. And I'd say, yeah, VLM, very uncertain and difficult to quantify that uncertainty. And very difficult to validate as well. For thermospheric sea level rise, so the global mean thermal expansion, it's a lot better understood. We know that thermal expansion is quite well represented by the global climate models. You can come up with a good estimate of the range of possible thermal expansion coefficients based on the global climate models and based on historical sea level rise, relating that to ocean heat content changes. So there is some way to use historical observations to tell you something about that thermospheric sea level rise. Yeah, so it's a lot better understood, a lot easier to quantify the uncertainty. It's an important process, but the uncertainty is smaller than for the ice sheets, for example. For some other smaller components like land water storage, the fact that we're storing more water on land behind dams, for example, is relatively small. So we should take it into account, but it's not a massive source of uncertainty. So then that leaves the ice sheets, which then leads back to your first question of how do we project the ice sheets? What's the best way? What drives differences between alternative methods? Now, the ice sheet models are good, I think, and they're getting better. I'm not an ice sheet modeler, so I'm sort of looking in a bit as a non-expert from the outside. But my impression is that there's been less resources devoted to developing ice sheet models compared to global climate models. So in some ways, the maturity of those ice sheet models is still behind the global climate models, although the ice sheet modeling community is doing a great job at improving them. Now, the challenge is that there are possible processes like this marine ice cliff instability that could lead to rapid sea level rise that one research group in particular has incorporated into their model. That leads to workflow 3, which is the highest of the model-based projections. The problem is that other people within the ice sheet modeling community maybe more skeptical that this is really an important effect. There's no agreement for how to model it, how to account for that uncertainty. And so the research on things like these faster processes is a bit more controversial, and hasn't really made its way into those large sort of mainstream ensembles that account for better understood processes. Another challenge is that it's very difficult to use historical observations to constrain these ice sheet models. I mean, we can look at things like paleoclimate. We can see that there were significant, uh, I mean, 120 meters, right, since the last glacial maximum. So we know that periods of warming compared to colder periods do lead to large changes in the amount of land ice. But the problem is that those ice sheets that have melted since then are different from the Greenland, East Antarctic, and West Antarctic ice sheets. And West Antarctica is quite different from East Antarctica. Greenland's quite different again. Um, so yeah, difficult to model, difficult to constrain the models. That's where experts can contribute something. So some of these ice sheet experts think higher uh, melt rates are possible. But then others would argue that the experts may be overestimating the uncertainty range. So yeah, it depends who you ask, as to who, whether they believe the models more or the experts more. We're trying to say they're complementary and we can combine the strengths. Yeah.
So it's interesting, Benjamin, because the low confidence of the expert judgments actually come from the expert who they don't trust the ice sheet model to some extent probably. So that's probably what happened, is it?
Now that's a good question. I think that may sometimes be the case. And I think that would really explain the results. Um, but I've never actually asked any of the experts who contributed to the IPCC structured expert judgment study that was led by Jonathan Bamber and others in Bristol. So I don't know for sure. There's also questions perhaps about uh, how, as an expert, you estimate probabilities. Because if you're an expert in a particular process or area of climate science, maybe you don't have as much expertise estimating probability distributions though. So there's lots of things that can be contributing to what might cause that discrepancy between the experts and the models. Um, Interesting question.
Okay, Benjamin. Thank you so much for the explanation. Okay, let's go to the floor. Ladies and gentlemen, if you have question for Benjamin, please you can use the hand raise feature, or maybe you want to write in the chat box also. Okay. Uh, so anyone with question for Benjamin? Okay. Yeah, I have a lot of question actually. Maybe I can post one more. How do you define the location that you are using for the coastal series in your plot right here?
Mhm.
Based on some in situ measurement, or is it the refer to the cities itself? Uh, yeah, maybe you can tell us.
Great question, actually, and a technical question as well. So That's something we've really wrestled with. So the short answer is that for this plot that we've included in this paper we've submitted, we used the IPCC projections on a 1 by 1 degree regular grid, and then just found whichever grid location was closest to any given city. Now, as we were doing this research, though, there was a point when I was mainly using data from the nearest tide gauge location. And this is where it gets a bit technical, because the IPCC relative sea level rise projections, there's sort of two lots of locations. One of those lots of locations is the tide gauge locations. And at those locations, the vertical land motion projection is more strongly constrained by the trend in the historical sea level changes recorded at that tide gauge. At the 1 by 1 degree grid box locations, which I now use, the tide gauge data is and trend is sort of taken into account, but it constrains the projection a lot more weakly. The reason why I'm now using these 1 by 1 degree locations is because I feel a bit more comfortable with the ability of those projections to capture those regional, larger scale trends. And I would have questions about whether the more constrained trend at a tide gauge is representative of a nearby city. The other challenge is that we don't have tide gauges globally, so doing it this way enables us to cover all major coastal cities.
Okay, thank you, Benjamin. Okay, maybe have question from the floor. You
Mas Yuda.
can. Okay. Oh, Pak Edi. Okay, please, Pak Edi.
Sebelum saya ada tuh siapa tuh?
Oh,
Oh iya, saya Mas.
Saya nomor
oh,
2 saja.
okay. Pak Tubagus, please go ahead, Pak.
Yes, thank you. Can you hear me my voice, Mas Yuda?
Yes, go ahead, Pak Tubagus.
Okay, thank you. Thank you very much, Benjamin, for your talk. It's very interesting. It's very nice, and although it's a bit more complicated for me, but it's okay. I just want to confirm something. So we often hear regarding the sea level rise, the terminology sea level rise projection and sea level rise prediction. I think these both terminologies are quite different. So I just want to confirm something. What is the difference? What is the difference between prediction and projection? As my understanding, prediction is calculated based on historical data calculation using satellite data corrected by tide gauge, and also take into account the vertical land motion. And the projection is calculated or fuse any components that you mentioned. A lot of things, Greenland, West Antarctic, East Antarctica, and also land water story, and so on and so on. That's the first question. I just want to confirm between the sea level prediction and projection. And the second thing, about the local relative sea level rise. Let's say if we want to map or to if we want to map the coastal flooding or coastal inundation in the particular area, let's say in the on the north coast of Java, which one better in your opinion? Is it using sea level prediction that I mentioned in advance, like using historical data calculation, or using sea level projection based on IPCC modeling? As you mentioned, it's there are some scenarios, SSP1, SSP, and so on and so on. That's my two questions, Yuda. Thank you.
Okay, thank you, Pak Bagus. Please, Benjamin. Yeah.
Yes, thank you for those questions. I don't know the formal definition for prediction versus projection, but I think you got at it actually when you're talking about whether you're predicting based on historical through to the present, or whether you're projecting long timescales in the future. So generally, the way I think about it is we predict specific events. So weather, for example, we have numerical weather prediction models, NWP. So generally in English language terminology, at least, we tend to think of prediction as often nearer term, trying to predict specific events, probably in a chaotic system. So sea level prediction from this perspective might be trying to predict whether a tropical cyclone might affect sea level along a coast next week, for example. When it comes to climate projection, though, we're looking at much longer timescales. We're looking at how the statistics of the system are changing on very long timescales. So we're not saying, we're not going to predict that a particular weather event happens on the 18th of November 2095, for example. Instead, we'll be projecting, or will tropical cyclones in general look different in 2095? So the same with the sea level. We're looking at those long-term changes in the mean and potentially variability. And projection, I guess, sort of emphasizes it's a bit, it's not quite as precise as prediction. We're not predicting anything specific. We're projecting what could happen and what the uncertainty range is. Now, for coastal impacts, again, the question would be what timescales you're interested in. If you're trying to come up with a extreme warning system for extreme weather or extreme sea level that gives you a warning a few hours, a few days ahead, then you'd need to have some sort of prediction system, and you don't need to worry about sea level rise. If, however, you're doing urban planning and you want to build coastal defenses to protect you from events in 30, 40, 50 years' time, then we need to use the climate projections because the changes in mean sea level are going to be really, really important, especially in this region where we don't get massive waves or massive storm surges. But projecting the mean sea level may not be enough. We also need to consider how it interacts with extreme events. So you would also need to take into account the present day tidal cycle, present day sea level variability, from things like storms and tsunamis, I guess, in this region as well, actually. Does that answer the question?
Pak Tubagus? Halo Pak Tubagus?
Iya, yes, Pak. Okay, yes, okay for now.
Oke.
Yeah, we can continue for the next question.
Oke, thank you Pak Tubagus.
Yeah.
Let's move on to the next one. Pak Edi, please Pak Edi.
Okay, thank you very much, Dr. Yuda. Hello, Dr. Benjamin. How are you?
Doing well, thank you, Dr. Eddie.
Thank you very much for your nice presentation. I think it is very, very useful for us, at least to save more than 2,000 small islands in Indonesia. But we don't know when will be disappear that those all small islands. Okay. I'm going to start my first question from the first. May I ask you and about the accuracy of your model? Accuracy of your model. I mean that have you compare with the in situ observation? Yeah, first about the accuracy. The second and about the in your presentation, I found you fully concentrate to the mean sea level rise. May I asking you exactly? I think we need to consider not only sea level rise, but also land subsidence. So combination between sea level rise and land subsidence coming simultaneously together is very important to be modeled to make the model not only sea level rise. Sea level rise we can taken from the satellite maybe, but for land subsidence, I don't know how we can obtain the data. Why we need to consider combination both phenomena? Because the impact will be more secure, will be more larger than only one parameter that we consider rise. So if you have already have that model, maybe we can apply to, for example, Jakarta sink. Jakarta is sinking. Then not only until 2100 ya. It's too long. We need more. I think 2050. And that model can be not every 10 years, but every 2 years or at least for 5 years. So this is the last. In your presentation, when you presented about the sea level rise, we found some area include Java, Sumatra, Kalimantan, but not for Sulawesi. Why? Sulawesi is looking free. It looks free. Similar question might be when you mentioned that the high impact. Why only not why Australia is looking free from the sea level rise? Shall we move to Australia and not here, not stay here? Okay, that's all my question, Benjamin. Thank you very much.
Thank you.
Yeah.
Thank you, Dr. Eddie. I think there's three main questions there, and I'll tackle them in reverse order. So this slide, which is up, you are very observant in that you did notice, yes, Sulawesi, I think it's 1 point at most along the coast, and Australia, just a small
No, first,
handful.
Australia is the first slide maybe.
Ah,
First slide.
I
First slide.
see. Okay, let me go back to that one then.
Nah,
Here.
here. Why?
Ah, this is,
Sulawesi is free.
yes.
What
So,
happened? What happened?
so here, there is it's difficult to see, but there is small portions of thin blue lines along the coast for Sulawesi. What this tool that I've used here to produce this map, it is produced by Climate Central. You can just do a Google search for it. It's free to use, and it's their coastal risk screening tool. And for this, they've just used the digital elevation map. And then you just put in a sea level rise number, and then they look for elevations that are below that sea level rise level, taking high tide into account, and whether that land area would then be connected to the ocean, so liable to inundation. Now, as I understand it, what would make a massive difference here is the terrain and the elevation. So these areas that we're seeing quite large blue patches, they're very low lying, river deltas in particular. So they're quite liable to flooding because the land is really low, going in quite far. For Java, actually, and for parts of the Malay Peninsula, you see that just the small area around the coast is vulnerable, but it doesn't go far inland, largely because there's a lot more hills. The terrain is not as flat at the coast. So I'm not very familiar with the terrain in Sulawesi, but I understand it's mainly sort of mountainous rainforest. So
No,
if
for example, Makassar City. Makassar is located in the southern of Sulawesi,
yeah.
perpendicular with the south with the ocean. Yeah, big ocean, I think, but still it's looking free. The other one is about the southern part of Kalimantan, because the peatland area is very, very large there. So I think that about that your model. So why I'm asking you about the accuracy, because it is due to the local impact maybe. Then the other one is we need to consider about the elevation of that area, elevation, and yeah, the type of the land, hard or soft, and etc. So it is my a little bit wonder about the model, and the other ones about when you mentioned about the last slide. uh, I a little bit wonder why uh, Australia is similar with the Sulawesi free. So the accuracy model is very, very important for us. Thank you.
Yes. So, so the answer will be different for these two different slides. So here, as you say, elevation's really, really important. And this slide is taking the elevation into account. But again, when you're zooming out at this level, it's just difficult to see that actually most of these coastlines, including around Sulawesi, do have areas along the coastline which are blue and vulnerable to inundation. So this tool that, as I say, is freely available online. If you put in a sea level rise projection, you can then zoom in to see how vulnerable an area is based on its current elevation. For the projections that we've produced, there's something else going on for Australia and Sulawesi, and it's because of the fact that here I'm only plotting locations that have cities around them. So in this particular study, we've just focused on cities. So large parts of the coast here in Australia, most of Sulawesi and many of these other islands in Indonesia, they don't have large coastal cities. So that's just why they're not shown in this map. But we can do projections for those other locations, and they would be quite similar to the projections that are shown here. So that's the third question, I think. For your second question, let me find it, which is you were emphasizing the importance of vertical land motion and subsidence in cities. I fully agree with everything you said. For a global scale study like ours, we can't look in detail at land subsidence at any given location. But I do want to emphasize, and as a research group, I think we'd want to emphasize that it's really important that there are more local and regional scale studies that zoom in on this challenge of land subsidence, either at the city level or at the island level or regional level. I do have colleagues who are looking at the earthquake impact. There was a study that came out from some other colleagues a few years ago looking at using satellites, INSAR radar to try to look at how subsidence is varying across different cities, including Jakarta. And it is true, as you say, that some parts of the cities are sinking so fast that actually subsidence is the major problem for that city, and sea level rise currently is far, far smaller. So if you're planning coastal defences for the next 2 or 3 or 4 decades or government policies, subsidence is going to be the main thing to look at. If we're looking at sea level rise on longer timescales out to 2100 or the second half of the 21st century, I think then we also need to pay attention to changes in mean sea level. And that's going to be important for many small islands, as you say.
I'm sorry, Benjamin. How much, which more give more contribution, land subsidence or sea level rise?
It depends on where you are. In Singapore, where I am, sea
Yes.
level rise is more important than subsidence.
Oh,
I understand that for Jakarta at the moment, subsidence is the city is sinking faster than sea levels are rising. So the answer depends on which city you're looking at.
yeah. Yeah, because now we are very interested how we can save the Bali island from that. Bali is a small island, very important. Maybe
Yes.
I think you have already gone to Bali, so of course,
I have, yes.
yes, that's right. So we are very interested how we can save Bali island from the land subsidence and sea level rise.
Yes.
Okay, I think it is yeah, enough my question and my comment. Thank you very much again for your nice.
Thank you, Pak Edi.
Thank you.
Thank you, Dr.
Thank
Edi.
you. Okay, anyone else? Questions for Benjamin?
Sudah?
Pak Bagus, okay. One more for Pak Bagus. Go ahead, please.
Yeah, sorry. So I was using my mobile phone. Now I'm using my laptop, so I can on my camera. I just want to add more information regarding Prof. Edi question about the Sulawesi and other areas in Indonesia. Is that okay, Benjamin?
Yes, please go ahead. Yeah.
Okay. So, Prof. Edi, so we can answer your question based on two aspects. The first aspect is geodynamics, and the second aspect is coastal characteristics.
Oh.
So yes, geodynamic. If we divide Indonesia into three zones, so the first zone is the first zone is Sunda Self. It's in the west, on the western part of Indonesia. The second zone is on the east, Sahul Self, Papua, and so on. And the third zone in the middle, in the transition. It's include Sulawesi, Bali, and the Lesser Sunda, Bali, NTB, NTT, Maluku, and so on and so on. So if we look at this geodynamic, so on the western, Sunda Self is experiencing subsidence. Regionally is experiencing subsidence. Going to the east, on the Sahul Self, also experiencing subsidence. While in the transition, we call it Wallace line. It's experiencing uplifting. So that's why we cannot we don't see the bright blue color here on your presentation, Benjamin, because in the transition zone, Sulawesi, Lesser Sunda, and other surrounding areas is experiencing uplifting. That's the first thing. The first aspect is geodynamic, and the second aspect is coastal characteristic. So on the transition zone, mostly the coastal characteristic are cliff and marine terrace or coral reef terrace. So it's high elevation, as you said, Benjamin. So because on the transition zone mostly is elevated coast. That's why also in Makassar we don't see the low lying coast, because naturally, geodynamically, Makassar is experiencing uplifting. Also, although it's the rate of the uplifting varies in every single areas. That's my what I say. That's my 2 cent opinion. My 2 cent opinion based on your question, Prof. Edi. And one thing that also I want to confirm you, Benjamin. Have you involved the vertical land motion in your model? That the first question. And the second, because you also discuss about IPCC model, have IPCC also involved the vertical land motion into the sea level rise modeling? That's my question. Thank you.
Thank you, Tubagus. Is that right? Yeah. Thank you for the explanation. That was, yeah, really helpful. And in answer to your question about VLM, vertical land motion, whether it's included, the answer is yes and yes. Because the IPCC did include it, and we are building our projections on top of these IPCC projections, trying to come up with complementary strengths. So in this slide showing the different parts of the fact framework, this particular box here in the middle, there's COP14 vertical land motion, is because the vertical land motion component came from a paper method that was developed by Bob Kopp and co-authors in 2014 that basically used a Bayesian model to try to come up with the different components of vertical land motion trends, and they were constrained using tide gauge data. Yes. Though the two caveats I would say with this are firstly, this approach assumes that we can just extrapolate historical VLM trends into the future, which many people, myself included, would question. And secondly, there's a question about how representative those tide gauges are. So I think there's a lot more work to be done on VLM. We can do much better in individual cities. We need those detailed studies. But for a global study, I think what's available in the IPCC is really good use of the available data.
Thank you. Yeah, thank you.
Okay.
To Dr. Tubagus. I'm sorry, Pak Yuda.
Yeah, please, Mary.
I'm sorry, Benjamin. Bentar. I think I am agree with you. I found here that in the presentation of already presented by Dr. Benjamin, climate central coastal risk screening tool, I think doesn't consider about the type or the characteristic local area. It is just global. So just to this is the instant how we can predict what happened in Indonesia or in another country, especially Southeast Asia country, especially Manila, Bangkok, especially Manila, Bangkok, and small how the impact of sea level rise until 2100 it is the pathway so to check the accuracy to check ini, yes, I am agree with Dr. Tubagus to consider about the local impact or the for each area, not can do uniform for all location, I think. Yeah, Dr. Benjamin. I'm sorry, I talk too much here.
Okay.
Not at all, Prof. Eddy. I really appreciate this interaction that we're having. And yeah, and thank you, Dr. Tobagus, for your earlier comments about this map. And I think as Dr. Eddy, as I understand it, is saying, yeah, for this map, things like the rate of subsidence is not being taken into account here. It's just assuming, in this case, what would happen if you have 2 meter sea level rise across this region today without any other changes. But the coastal characteristics that Dr. Tobagus mentioned would be taken into account because this map is based on a digital elevation model. So it's looking at how high the terrain is, especially near the coast, and then also whether the low terrain is connected to the coast. If one area floods, can it spread to another area? But I think as you're saying, Dr. Eddie, if I understand, something like this is really just giving you a big picture overview. It's designed to be a global scale screening tool. It's great, I think, for something like a talk or if we're wanting to identify which areas to zoom in on. But I think that locally, you can come up with much more rigorous assessments using more detailed digital elevation models that may be available for individual cities. So for detailed city scale studies and detailed scientific research, I think absolutely do something that really takes the local context and expertise into account.
Okay, it is the last for Benjamin. Are you agree with the giant wall to save Jakarta from sink? Giant wall is very, very large, very, very heavy. Why not back to natural to save this? What do you think of how we can protect, how we can reduce the impact of the sea level rise? I don't think so, but I don't think that giant wall over Jakarta is the best way, the best option to protect Jakarta from the sinking. Thank you. Sorry, Benjamin.
So I would defer to your expertise on that, Prof. Eddie. I'm not familiar enough with the Jakarta coastal defences to really comment. I'm also not an engineer, and I'm not an urban planner. I just look at what's happening to the climate system and what might happen to sea level in future. And then urban planners and coastal engineers, practitioners need to make very difficult decisions based on that information, taking many different things into account when they plan coastal defences. I do think, though, that there is a place for hard coastal defences. If you really want to keep rising sea levels out, and especially if a city's sinking, it's difficult to do it using just natural nature-based solutions, though they can play a role. But it's complicated. Sometimes retreat from the coastal areas might make sense, though we can't do that in Singapore because we don't have anywhere to retreat to. So it really depends on the context, I think. And if there are ways to reduce the subsidence through stopping groundwater withdrawal, of course, things like that could actually be the priorities, maybe. What do you think?
We need more deep analysis, but the key point is how our model can be working very well, especially for the extreme condition, especially for the localized area, especially for how we can save more than 2,000 small Indonesian island for next several years later. So I think what you have already done is very, very useful for us. We need to combine what we have done. For myself, I try to make that model is a combination between cerebral rise and then subsidence simultaneously, and we apply to the coastal area. How many percent that area has already will be covered by sink 2030, for example, 2050, and etc. So the key point is the model. Of course, we need to consider what already recommended from IPCC. Yes, But the small island for Indonesia, we need again and again discuss and more. Not only enough one seminar or one deep analysis, deep deep statistically and etc. Model is now to save our time to protect Indonesia is small country, unique country, very big country, and more than 5,000 island. Anyway, anytime, next time, please come to BRIN in Bandung. We can discuss here, Dr. Yuda, me, myself, and all young scientists from BRIN. I think, of course, I believe they will support you to join with us. Thank you very much.
Okay, Pak Edi, I think let's we still have one person raising hand. Randy, please go ahead, Randy.
Thank you, Mas Yuda. Hello, Benjamin. My name is Randy. I'm still student. Yeah, thank you for a very great presentation. I have a question about the result. You show the picture about the high-end projection in major city. Can you back to that slide? Thank you. Yeah, this one. As we can see in this figure, you mentioned that the previously you mentioned the high-end projection in the major megacity in Asian. It's related to the particle length motion and also something about the GRD or ice sheet. And I'm just curious. How you treat the sea level component in your model that you come out to the conclusion that the high-end projection in the megacity in Asia mostly by particle and motion and also about the ice sheet. And for particle and motion, I think we can agree that most of the megacity experience the particle land motion due to the uh, freshwater usage. But for the ice sheet, I don't know how the polar region can influence the tropical region, something like that. Can you explain about this one?
Yes, thank you, Randy, for the question. And so, if I understand the question is how do the ice sheets influence this region, and especially in this high-end projection? Now, the ice sheets dominate the high-end worst-case projection because of the fact that the ice sheet components are dominating the total uncertainty range, and then they're responsible for a lot of the sea level rise at the top end of the uncertainty range. And then in our worst case projection, we're looking at that top end of the uncertainty range. So this is why the ice sheets are really important for the high-end worst-case projection, but the ice sheets are making very little contribution to the low-end projection. So they're just really important if we want to consider worst-case possibilities. Now, when the ice sheets melt, that water is added to the ocean. And it's reasonable to think, and to a good approximation, it's true, just to think that that water will just spread everywhere equally around the world. And that is almost true. but it's complicated by these GRD effects. So the G is for gravity. The ice sheets are so massive that they actually exert a gravitational pull on the nearby ocean. So they pull water towards them. So if you're losing water from the ice sheets, you're sort of losing a bit of that gravitational attraction. So you're pulling a bit less water towards the ice sheets. So therefore, the sea level rise is not equal everywhere. The rotational effect is to do with the fact that they can change the Earth's rotation, which affects the distribution of water a little bit. The deformational effect is really important, especially locally, and that's the fact that the ice sheets are sitting on this land, so they're pushing the crust of the Earth down, and then as that ice melts, the crust of the Earth can rise up a little bit. And we're still seeing some of the long-term relaxation of the Earth's crust following the loss of the ice sheets during the last ice age. So this operates on lots of different timescales. But if the ice sheets and the crust is bumping up again where the ice sheets were, then that means more water is pushed away from that location. So in the tropics, or in Singapore at least, and I think the numbers would be very similar for Jakarta, the amount of water that we get from the ice sheet melting is about 10 to 15% more than the global average. So if you get 1 meter of sea level rise from the ice sheets, you'd get about 1 meter and 15 centimeters, 1.15 or 1.1 meters of sea level rise from those ice sheets in this region. Does that answer the question?
Yeah, okay. Thank you very much for your clear explanation.
Okay, thank you, Radley. We still have a few minutes. I would like to follow up a little bit, Benjamin, what Rani just said. Sometimes if we concentrate in regional climate, we are doing some kind of bias correction. You can correct for various atmospheric climate parameters like surface temperature or including maybe the SST and all the other components. And if we refer to the step-by-step procedure of those sea level modeling, you need that climate model to drive the other components, including the ice sheet and so on. So if we do the correction, let's say in our region here in maritime continent, should we rerun those process again? And I mean, is there been any feedback if we change the like small part of the global climate and we want to do sea level projection in that region? So maybe that's yeah.
Yes.
Is there a feedback to the whole process itself?
Mm-hmm. So depends on the process you're looking at, I think would be the answer. So for the ice sheets, the regional effect, you can just scale using what we call these GRD fingerprints. So as I say, for here, it's about 10% more than the global mean. There's no sort of really detailed study needed. It's quite a similar fingerprint across this region. For thermospheric, it can be useful to do regional scale studies because of the fact that it ties in with dynamic sea level as well. So if you're getting changing circulation patterns, changing wind patterns, changing heat transport patterns, that can mean that you get dynamic sea level changes which are different from the global mean. So one way that's sometimes done is just using GCMs, but there's scope to use higher resolution regional ocean models as well. I think this is valuable, especially if you want to understand heat transport and regional climate change. It's not going to make a massive difference, though, to the estimates of the total sea level uncertainty, because that component tends to be a bit less uncertain anyway. What really makes a massive difference for detailed local, I guess, downscaling studies would be the vertical land motion. So if you really want to focus on one thing that would bring a lot of added value to try to understand sea level rise in a given city, it would be to use a locally derived vertical land motion component or vertical land motion model based on what you know about sea level rise in that city or region. And then you can use the IPCC for the other components, or use our fusion projection for the other components.
So you can combine between the vertical land motion derived from the local observation with what IPCC procedure is, as you explained just now, to give
Yes,
like more trustable projection.
that's right. That's right. And from a data user perspective, all of the IPCC projections are available without the vertical land motion component. And we're also making our fusion projections available without the vertical land motion component. So what this means is you can easily combine, sub in your own VLM component.
All right, all right. Okay, Benjamin, thank you so much for the answers. And I think we are coming to the end of our forum here. It's already 3 minutes. Here in Bandung, in Singapore should be 12 something, should be lunchtime for Benjamin. Let's not hold back. uh, Thank you so much, everyone. I wonder if Pak Sulaiman still around, maybe not. So
Pak
maybe
Yuda, maaf
yes,
sebelum
Pak Edi.
ditutup, itu materi presentasinya bisa di-share atau bagaimana? Supaya ada
Okay, we can check.
untuk barangkali nanti ada pertanyaan atau itu bisa sampaikan ke Benyamin gitu.
Right, Benjamin. Does your presentation? Can you share the materials? Because I know it hasn't published yet. Some figures there. If you can just email me, and we usually will put the link in the YouTube live description. Is it okay like that, or?
Yes. Yes, I think that would be fine. So I can email
Okay,
that
that's
to
great.
you
That's great.
after
Yeah,
this. Yeah.
yeah.
Mhm.
Just
Thank you.
email me, and then I will. Pak Edi, nanti bahan materinya di deskripsi YouTube live-nya, Pak. Nanti bisa di-download di situ.
Ya, linknya saja nanti ya
Oh iya,
Benyamin
ya. Bisa, Pak.
link
Okay.
we can download.
Okay, yeah. Benjamin allow us to get the material. Okay. I think I will close this forum. Thank you so much, Benjamin. It's been a pleasure to host your talk today about sea level, and everyone here. Thank you so much for all the questions, all the interactions. Really appreciate it. And we meet again in the next Colloquium Prima. So thank you, and goodbye, and have a nice day. Thank you.
Thank you, Dr. Yuda, and thank you everyone else
Yeah.
for the
Thank you, Yuda.
interaction.
Thank you, Benjamin.
Thank you, everyone. Thank you, Randy. Okay, I will. Let's leave this.